Good morning. So, it looks like we have a pretty light crew. That's okay. So, how are you guys doing? Are you hanging in there? We're going to talk about energy conservation some more today. Yeah, I'm doing okay. I think the all screens all the time is definitely it's kind of it's kind of wearing, it kind of wears you down after a while, um but we're getting there. We're in kind of the last lap. We're getting towards the end, so we have a few more pretty interesting things to talk about. So that keeps me um, engaged, and it's cool watching you guys show up 8 o'clock in the morning. It's tough uh, to watch stuff on the internet, so I appreciate it. Um, Hi, Carolina. So okay, we'll see. Maybe we'll get a few more folks to jump in. We're going to talk about basically three things today. Um, well, we'll see what all we have time for, but energy conservation with non-conservative forces. So basically, yesterday we talked about situations where we just had mechanical energy. So let me recall. We talked about mechanical energy, uh, which was just the sum of potential energy and kinetic energy. So that was sort of the energy that we can write down an expression for what that is as a function of position um, and velocity. Well, uh, energy conservation in general is going to encompass more than just mechanical energy, and so this is basically the next couple sections, 8.5, 8.6. So see 8.5, 8.6. And the idea is quite simple to state. Um, so momentum will be in the next chapter, I think. So this doesn't have too much to do with momentum. Um, Energy conservation in general, there's more than just mechanical energy, right? So the way that I think is useful to think about this, or that's pretty um, maybe a good way to kind of keep it organized, is if you look at the energy, uh, mechanical energy that you start with, it's going to equal the mechanical energy that you end with. So far, those are provided there isn't any friction or anything like that. But if there are non-conservative forces present, if there is friction, drag, uh, then this isn't going to be the case. You may end up where you have mechanical energy um, final is less than what you start with. And in this case, energy has gone into non-conservative, into work that's been done by non-conservative forces. So, and the one at the top of our list is, friction. And so getting a handle on how to incorporate this into solving problems will be very useful for you. There are definitely a few problems in the homework set that involve, oh, what if there's friction now? It makes things a fair amount more complicated. But just to kind of lay it out, what it would look like is kinetic energy initial plus potential energy initial, i.e. mechanical energy initial, is going to equal kinetic energy final plus potential energy final plus some work that's been done by friction. Okay. So let me show you an example to kind of give you a feel for this. Got some examples going on here. I think there's a skier problem in the homework assignment as well, if I recall. Wait a second. Oops. So here you go. This a little bigger here. So a skier starts from rest and slides down a 28 degree incline, 85 meters long. If the coefficient of friction, mu k, is 0.09, what is the speed at the base of the incline? And if the snow is level at the foot of the incline and has the same coefficient of friction, how far will the ski travel along that level? And we're going to use energy to talk about this. So, before we could have looked at problems like this with kinematics. You could imagine summing the forces and finding the acceleration, and then, the distance, the acceleration. You could use your formulas for velocity as a function of distance and acceleration to come up with the velocity and figure out how far it's going to go, etc. But we want to think about this in terms of energy, and in some ways it's a lot easier to kind of keep track of, I think. But the first thing we would do is going to be similar. Let's give ourselves a picture here so we can kind of see what's going on. So we have an incline. Trying to draw this a little bit nicer. We have an incline, 28 degrees. Apparently this incline is 85 meters long. We know that the coefficient of friction is going to be 0.09. And we want to know, first of all, what's the speed here? And then we also want to know, how far is it going to go? So we need to actually lay out a couple things. So let's break this up into 3 parts again. We have our skier up here. So in other words, let's say this is 1, the bottom of the hill will make 2, and at their final, stopping position will make that 3. And in terms of our expressions for energy, what we will have is the potential energy initial. So I'll just write it all out. Some of these are going to be 0, and we can talk about which ones are going to go away. So actually, let me phrase these in terms of our numbers. So the potential energy 1 plus kinetic energy 1 is going to equal the potential energy 2 plus kinetic energy 2 plus the work that's been done by friction. Okay. So in order to figure out the speed at the bottom, we're going to have to account for the potential and kinetic energy, both at the top and at the bottom, and also the work that's been done by friction. And the potential energy, initial, generally that's going to be mgh for these kinds of problems. We're talking about gravitational potential energy, right? We're concerned with the height. So we'll have to figure out what that height is in terms of this angle in a second. Kinetic energy initial, well, it's not moving. He's starting from rest, so this will be 0. The potential energy at the bottom, we can set up our coordinate system with the origin at the bottom of the hill. This will simplify things so that at the bottom there will no longer be any potential energy because there's no longer any height. The kinetic energy at the bottom is what we're after. So that'll be 1/2 mv, let's call it v2 squared. Plus work that's been done by friction. Well, the work done by friction, recall, is going to be the force of friction times the displacement. Now, generally, the work would be F dot D. We're going to, let's convince ourselves that these are in the same direction, so we can just write it as FD. So to do that, in order to figure out this work, we're going to have to pin down what the force of friction is. So we have to do ourselves a favor here and create a, let's make a quick free body diagram of the skier just to lay out the forces in play. So recall, he's going to have some weight. Oh man. There's going to be a part that's along and a part that's perpendicular. He's going to have some normal force. And really, the only part that we're interested in is the normal force, because the normal force is what we need to calculate friction. Remember, the force of friction is mu times the normal force. So we need the normal force. Well, the normal force is going to be the component of the force of gravity that's perpendicular to the incline, g cosine theta. And so if we quick sum the forces in y here, here, let me write this over here. You have the normal force, you have minus mg cosine theta. That's going to equal 0 because the acceleration in the y direction is 0. Let's see, can we factor out an m? It's likely, yeah, that we'll have an m that cancels or something like that. Let's see. We'll see. We should see that fall out once we get it all set up. So this is just sort of, this is sort of necessary background, just to get us to the point where the normal force is mg cosine theta, and then notice that the force of friction then would be mu k mg cosine theta. And that's this ingredient that we need for here to calculate the work. We need that ingredient to calculate the work done by friction. We need the force of friction. Okay, so let's see. The other ingredient that we need is we need to know this height in terms of the angle. Well, we know the distance, the hypotenuse in other words. So we can get the height from d sine theta. So let's call this r, say. Then h here would be r sine theta. So putting these ingredients in, we'd have mg r sine theta is going to equal 1/2 mv2 squared plus our force of friction mu k mg cosine theta d. And I was talking about the dot product. So notice the force of friction. I didn't put the force of friction in. The force of friction would be along the incline, right? The displacement is along the incline as well, so they're parallel, so we don't have to worry about computing the angle between them because they're in the same direction, or they're in anti-parallel directions. Okay, so we have those components in. We have the height in terms of the angle. We have the force of friction. And we could then solve this expression for v, because recall what we're after is what is the speed at the base of the incline. So let's solve this expression for v. Let's see here. We'll have, yeah, and Caleb, to your point, this factor of m would cancel. And we could then reorganize this a little bit. So we would have a gr sine theta minus mu k g cosine theta. Wait a second. I kind of made I have two different variables for the same thing. Let me fix this. Let's call this d and this d2. So this force of friction would be times d. This would be a d as well, just to make things consistent here. D mu k g cosine d. So all that we've done here is subtract over this piece, and then we could multiply this by a factor of 2. And then we would need to take a square root, and this would give us v2. And if we, put all of our numbers in here, this would be, let's see, 9.8 times our 85 sine 28 degrees minus 0.09 times 9.8 times 85 times cosine 28 degrees. We find that this will give a V2 of 25.5 meters per second. So I think this problem is pretty helpful because it shows you incorporating the force of friction on an incline. And this was one of the more complicated things that we looked at when we were talking about forces, because you need to know the normal force. And that depends on the angle as well. So it gives us an opportunity to review that idea. But now it's in terms of work done by friction. So the larger context is energy. So I think that one will be pretty useful for you. And we can also, let's not forget the second part. We want to know how far he's going to go. So if we know the velocity at 2, we know the kinetic energy. If we know the kinetic energy, we can figure out how far he's going to go. So let's do that too. So part B, let me just lay it out here. I'll put in all the parts, even though many of these are going to be 0. So in other words, so there's still friction. There's still going to be work that's done by non-conservative forces. If we're on the level where y equals 0, there will be no potential energy at 2 or at 3. He has kinetic energy because he has this velocity, right, at 2. But when he finally comes to a stop, there will be no kinetic energy at 3. So basically, we're just seeing how that initial kinetic energy is converted into work that's done by friction on the flat. It'll be simpler this time because it's easier to calculate the work that's done when you're not on an incline, right? So this will be 1/2 mv2 squared is going to equal the work done by friction is the normal force. So if you're just flat, that's going to be mg times the coefficient of friction, mu k, times the distance. So then we can solve this for d2. Notice, yeah, again, our mass cancels. So 1/2 v2 squared divided by g divided by mu k. We put our numbers in here. We have 1/2 25.5 squared over 9.8 times 0.09. We evaluate that. You would find that this distance is 368 meters. Okay. So, like I said, I think this is a pretty useful problem because it kind of contains a lot of things. It gives us an opportunity to review the force of friction, find the force of friction on an incline. It's this idea that we're using in this chapter, introducing right now, that if you have mechanical energy that's lost to non-conservative work done by non-conservative forces, you can add it in and figure out quantities like distance, speed, when some of the energy has gone into work done by non-conservative forces. How do you feel about that? Questions on this guy? Relatively complicated question, but it does definitely synthesize a lot of things that we've been doing, so I think it's a good question. And I think there's one that's pretty similar in the homework set. Let's see, how are you doing, Carolina? Who else do we have here, actually? So, sure. Yeah, I think working through, like I said, there's a question in the homework that's pretty similar to this that'll give you a chance to exercise this. Okay. Let me show you another question, another example. So the other example that I wanted to show is come on, is this one. So this is similar in that we're going to have some work that's done by friction. So we have a 180 gram wood block that's attached to a spring, and the block can slide along a table where the coefficient of friction is 0.3. And a force of 25 newtons compresses the spring 18 centimeters. If the spring is released from in this position, how far beyond its equilibrium position will it stretch on its first cycle? So this question is also I think, pretty useful in terms of the homework assignment because it gives us a chance to, or this one's also useful, to give us, to look at springs and review some of the things that we need to know to solve spring problems. So let's sketch this. What is going on here is, if I can sketch this. So it starts from equilibrium. So one of the things that's kind of confusing that we have to, I'll try and draw this as carefully as possible here, that we kind of need to get a handle on is, when we're talking about springs, it can have some length that's not 0, but that equilibrium position is really like the 0 for the problem. So we've talked about setting the coordinate system so that we have a 0 height that makes it easier to solve problems. This is kind of the same notion. If we start with the equilibrium position being at 0, then it'll make it easy. We'll measure from that equilibrium position. That way we don't have some offset, and it'll mean that it'll be easier to set up the problem. So what we do is we start at some equilibrium position, we compress the spring, God, if I can draw a square here. We compress the spring. Some initial x, let's call it x initial, and then we're going to let it go, and it's going to bounce back. There's going to be energy that's converted from this potential energy that we store into the spring into kinetic energy, and then eventually into potential energy again as the spring goes beyond its original position. And this final distance is actually the quantity that we're after. We want to understand how far does this go. Now, if there wasn't any friction that was present, what you would observe with this is that it would just flop beyond the same distance beyond its equilibrium position, and it would just flop back and forth forever if there wasn't any friction. So if no friction, dissipation, etc., this would be really easy because x final would be the same thing as x initial. But alas, that is not what's happening. We have friction present. So we're going to have to find the work that's done by friction and incorporate that. Okay, so let's set it up. The potential energy initial plus the kinetic energy initial is going to have to equal the potential energy. Actually, let me see here. Let's so I can label these again. Let's call this like 1 and 2, just so we have kind of keep track. So the potential energy at 1, or I think it's nice to have when we have multiple steps, and this is like what I did above, so we'll just do it the same way. The potential energy and kinetic energy initial at 1 is going to equal the potential energy plus kinetic energy at 2 plus the work that's gone into friction. So, okay. The potential energy, so initially, we just compress it, and then we release it. So in other words, it doesn't have any velocity the moment that we release it, so there won't be any kinetic energy. And then by the same token, once it gets to the very end, as far as it's going to go here, it comes to a stop, and so there won't be any kinetic energy at 2 either. So then we can put in our potential energy due to the spring. So that'll be 1/2 kx squared in general. Just to recall, potential energy of a spring, 1/2 kx squared. So this initial potential energy, the x will be x initial squared. That's going to have to equal the potential energy final, 1/2 k x final squared. Now notice that the sign of this doesn't matter because it's squared. So if we were being careful, this xi, it would be negative, yeah? So we could put it in there, we could not put it in there. And the only thing that matters is the how far it is from the equilibrium position, since the spring energy depends on x squared. And then also we're going to have work that goes into friction. So the work that goes into friction will be the force of friction times the total distance. And you can see here the total distance that we're doing friction over is going to be both xi plus xf. This whole distance is where energy is going to be going into work done by friction. So this will be the force of friction, mu mg, mg, times x initial plus x final. Okay. This is the total distance. Where we're doing work with friction. And so we can reorganize this. Recall, what are we actually after? We're trying to find x final. Notice this is kind of a little bit tricky. We have x final in more than one spot. So let me just reorganize this just so it looks a little more logical. I will order the terms from highest order to lowest order. So notice we're going to have I think you can probably see now where this is going. Oops. So I've ordered the terms counting from powers of x final squared, x final, and then some other stuff. So in other words, we have a quadratic. So in order to solve this, we would have to stick this into our quadratic formula, where this stuff in front of the x final squared this is our b, and then all of this would be c. Notice we know all of this stuff. One detail though, k. So what is k? We're not given it directly, but just to recall, k is the force per distance, and we're given that this was 25 newtons per, let's see, 18 centimeters, 0.18 meters. So that's how we would come up with a number for k. So we would need that here. but this is, you would then solve this in your calculator. You could solve it on MATLAB, use a quadratic solver, use that bit of code that we have way back from talking about projectile motion. You could use the same approach here to solve the quadratic. When you do that, you would find that x final is 0.17 meters. So I'll just put a note here. You could use the quadratic formula, MATLAB, etc. Whatever works best for you. And when you do that, you'd find that this x final is 0.17 meters. And this is, we can kind of check ourselves. So I told you over here that if we didn't have any friction, x final would be the same thing as x initial. So x initial was 0.18, and the distance that we found was 0.17. So since x final is less than x initial, this is what we expect. So this agrees with what we expect because some energy has gone into work done by friction. Yeah, so like I said, this is a good question because it gives us a chance to look at friction. It gives us, it's another example where we're looking at work done by friction. We get to review springs, and also it shows you that you can have, don't be alarmed if you run into a quadratic every once in a while. That can happen with this stuff as well. So what do you think of that? Questions on this guy? What questions do you have? So I think there is a question in the homework assignment that's very similar to this. What's the value of xi? So it's actually given to us. Yeah, so if this was on an incline, we'd have to worry about friction as well, or gravity as well. Yep. So let's see. Yeah, this xi is here. Yeah, if this was on an incline, we would have to account for gravity. Yep. So that would be an additional ingredient. And as we saw with the question up here, if we were worried about the incline, also the normal force would depend on the incline. It would be a little more complicated in that respect. So, okay. Or sorry for whipping that around. Other questions? So I want to talk about basically one major other topic and one minor topic in our last 10 minutes or so here. And that is the potential energy due to gravity. So this is a little bit changing gears. But this is the basically the next section. And so we've talked about potential energy due to gravity, but we've only talked about it in the context of, so far we've talked about this MGH. This is the potential energy due to gravity. But this is only valid when the change in height is small. Okay. Instead, consider what was our definition for potential energy? It was the negative work. In other words, it was the negative integral of force dot dl. And we have a different expression for the force of gravity when we're talking about things like satellites, right? So if we're talking about big changes in distance, mgh does no longer apply. And so we'll get a different expression. And so let's do that right now. So to do that, we need to integrate our force of gravity, which was, remember, big G mm over r squared. And technically then this would have a r hat, and we would be dotting this with dl. And really what that means is we would be looking at, recall r hat is pointing between. So the dl that we're concerned with would be pointing along the object between. And so in other words, it's up as we go up. So this becomes an integral of r squared, 1 over r squared dr. Notice the GMM is constant. We could pull that out if we wanted to. Why don't we do that just to make it a little more clear? Give us a little more room here. dr, so we're trying to integrate 1 over r squared is the short story. And when you integrate this, yeah, so the r hat dot dl becomes just, we're just integrating over dr. Or with the differential is dr, because dr points, in r. So when we go to integrate this, you probably have dealt with this function before. This will yield oh, sorry, there's a negative sign here too, right? So notice we pull this stuff out, this would become positive. You integrate dr over, or you integrate 1 over r squared. That's going to give you negative 1 over r. And you can confirm this to yourself, or you may think of it as r to the negative 2 dr. So when you integrate that you would add 1, right? So this becomes r to the negative 1. And then you would pick up also a negative sign. So notice then when you take the derivative of this, negative r to the negative 1 minus 1, you get back r to the minus 2. So, like we've talked about before, you can check, yourself. And recall, in general, this is going to have also a constant. And so our expression for potential energy is negative GMM over R plus a constant. And there's a convention for pegging what that constant is, and that is to say, make it so that the potential energy at r equals infinity is 0. So in other words, set C equal to 0 so that the potential energy at r equals a large number goes to 0. So this is kind of weird, maybe, because what this means is that the potential energy is always negative. And so we can plot this. It's going to look like the function 1 over r. So in other words, it looks like something like this. It goes to 0. Notice it's always negative. But this is a nice convention because then instead of it having some offset that you have to keep track of, you don't have to keep track of. And this also means that, if you're comparing different bodies, they don't have different constants because everything goes to 0 when you're sufficiently far away from it. So now I would note, if we had a little more time, you can actually show that this potential energy as a function of r goes to mgh when the change in r is very small. But you can show that with like a series expansion. So I may post an additional about a little bit about that. But we don't have time to talk about it in class. But you can show when it's really small with a Taylor series, which is kind of a cool application of sort of Calc 3 ideas. But that's sort of an aside that we don't have enough time to talk about. So one of the cool applications of this is something called escape velocity. So I'll phrase it this way. Maybe you get it in Calc 4. Yeah, it's a later Calc idea. It's definitely cool. Like I said, I might post a little bit about that. But let me show you one example with this idea. I don't want to abuse your time too much. So this potential energy as a function of r expression derived from the force of gravity is useful to calculate things like escape velocity. So escape velocity is a simple idea. That is, if you were to just shoot something up in the air, what velocity would it need to escape the planet and just keep going? So granted, this doesn't involve, we're not accounting for air resistance, so that's a big caveat with this. But in other words, what velocity, it would work for the moon better, say, right? If you don't have any atmosphere, this calculation would tell you how fast you need to be able, how fast you would need to be going to just escape the gravity. And it's an application of energy conservation. So what does it look like? Well, kinetic energy initial plus potential energy initial is going to equal kinetic energy final plus potential energy final. We're assuming that there isn't any friction or anything. And basically what this means is the potential and kinetic that you start with, when you're very far away, the potential energy is going to go to 0. Remember, like I explained up here, the potential energy when r goes to infinity, this is going to go to 0. The kinetic energy is also going to go to 0. So in other words, what this means is, you start with some velocity and then you go very far away. You're going to slow down, and once you get very far away, when r is big, the v is going to go to 0 as well. So this would also be 0. So then we can just plug in our expression for kinetic energy initial and our expression for the potential energy. So it's kind of weird, this thing that we haven't used yet, but gmm over r, negative, that's going to equal 0. So notice the mass is going to cancel. We can then solve this for v. This is going to be our escape velocity. So what would that be? We'll have g mass of the Earth, or whatever, planet, body we're talking about. We'll have a factor of r. Well, excuse me. And we'll pick up a factor of 2, and we would need to take a square root. And if you do this with the Earth, so if you put in the mass of the Earth, the radius of the Earth, you find that this is 11,200 meters per second. So in other words, 11.2 kilometers per second is the velocity you would need to escape the Earth's gravity. And the main reason that I'm showing you this is just because it's an application of the potential energy as a function of r due to gravity. Okay, so we're already over time a couple minutes. I don't want to spend too much more time. There was one topic that we didn't really get to, and that is power. Power, though, is really easy. You can read about it on your own. So also, power is just energy per time. So you're going to have to read about that. So if you do some joules of work in some period of time, you will end up with watts of power. Energy per time. And there's a question at least in your homework about that. So, and then this is in, I think this is in section 8.8. So, sorry we didn't have a chance to do a question on that, but I think that is a subject you're more than capable of reading about and calculating stuff with on your own time, or on your own, because it's pretty straightforward. It's pretty straightforward. You just divide, the change in energy by the change in time. Questions? How are you guys doing? It's kind of a lot of stuff, but this should give you everything you need, I think, to tackle any of the problems in the homework. I'm trying to be better about not stepping on the passing time, so I'll want to wrap up here. of course, if you have questions with the homework, contact me on Teams, post in Teams, and we can kind of have a discussion. Just shoot me an email. Questions? Questions? Sure. Yeah, if you have a question, ask me in Teams or post about it in the homework questions, and we can have a discussion there. And then, you know, we can kind of talk about it together. Ah, the spring on the slope. Sure, sure, sure. Yeah, that's going to be kind of a combination of the two problems that we looked at for most of class. So that could be, kind of there will be a fair amount going on with that. Yeah, we can look at that one. Other questions? You're not concerned about gravitational potential energy? I would read that section in your text. I mean, as well as the rest of the chapter, the entire chapter, but there's some good explanation in there about that. Other questions? You guys doing okay? Yeah, this last so the gravitational potential energy and escape velocity is 8.7, and then section 8.8 is power. Yeah, the power piece is kind of incongruous, but it's a good thing for you to know about. So, all right. Well, like I said, we'll talk about homework. We can talk about homework questions in Teams. And so have an excellent day. We will chat with you soon. Yeah, see you next week. Have a nice weekend.